So let us look at this relation or equation in x and y. So first thing to notice is this, that it does not give y as a function of x. And the reason is that if you go ahead and graph it, so here is a Desmos graph, and you can see that it does not pass the vertical line test, okay? But say we want to do this, we want to look at it locally. Locally means, near a point. So for example, say we look at it near 0, 1. Then what we can notice is that, we have a region near this point 0, 1, where the piece of the graph does pass the vertical line test, and there is another condition that it should not have any vertical tangent line anywhere. We are not going to go into that theory very much. So when that condition is satisfied, then what happens is this, that we can assume that for this particular domain here, I can write y as a regular function of x for this piece, okay? And what we say is this, that let me rewrite the point, that we can write y implicitly as a function of x near this point 0, 1, and with the conditions that I specified, that first of all, you have a smooth graph here, no vertical tangent lines, so y will be a differentiable function of x. And again, I'm focusing only on this piece, all right? So what we have is this, that 0, 1 is a point on this graph, and you can verify it by looking at this. That is, if you substitute y equals 1, x equals 0, what do you get? y1, x is 0. So what we have is this, that here we got 1, e to the sine 0 is e to the 0, that is 1. So this portion is 1, and this will be 1 times natural log of 1. Natural log of 1 is 0. So we do get, what we do get, 1 equals 1, okay? And so this equation is true. So now we did enough algebra with some calculus background. So let's go ahead and find equation of tangent line to a graph of this equation at the point 0, 1. So what we will do is, that is, we know that we have this, that is, y can implicitly be written as a differentiable function of x. So I can go ahead and differentiate both the sides with respect to x. So let's do so. So we got this, and then plus we have again the derivative of the second part with respect to x, and we are going to review product rule, chain rule, everything in this calculation. Okay? And I would try to make it not too fast, but not too boring either, hopefully. So here what we have is, we will first use the product rule. Okay, so when we use the product rule, what we get is that we got, you can go in any order you want. First, we are differentiating the first factor, leaving the other one unaffected. Okay, and then we are going to leave the first factor and differentiate the other one. Okay, so we got dx, and then e to the sine x, and then plus here we will differentiate y. So we got dy dx, and then this factor is unaffected, and then we have plus, we will have y, and then we are going to write ddx of ln of 1 plus x square. Okay, and on the right hand side we have derivative of 1, and that is going to be 0. So what do we get here? Here, the derivative of y is square, y is a function of x. So we'll just use the chain rule and write that as 2y, and let's write y prime for dy dx, okay? Just to save space here on our writing board. And then we got e to the sine x, and then plus we have y square, and derivative of an exponential is the exponential itself. And here, since I have function of x which is not identity, so we'll have to multiply by the derivative of this function, which is how much? Which is cosine x. So then plus we will write dy dx again as y prime, leave this as it is, okay, and then plus y times, now we are differentiating natural log of a function, so or natural log of a quantity, so what that will be, 1 divided by the quantity, and then by the chain rule, the derivative of the multiplied by the derivative of the quantity, which happens to be how much? 2x, and that becomes 0. So what we have is that if we just write it in a slightly more simplified manner, actually there's not much to simplify here other than we may write this 2x over here, okay? So right here we have y prime here. We can go ahead and solve for y prime if we would like, but what was our objective? Our objective was graph of or equation of the tangent line at the point 0, 1, right? So what we can do is that we can just go ahead and substitute x equals 0 and y equals 1 right here. So let's do so quickly. And if we do that, what do we get? Y is 1, okay? And let's just write this in a little formal way. You don't have to, but I'm just doing it here just for sake of clarity. So here we got this y prime at 0, 1, and then we have e to the sine 0. That will also become how much? E to the 0, and that is a 1. Then again we have a 1 square. E to the sine 0 will be 1 again, and this one, yes. So this is a 1 again, and let me write this formally as 1 for a moment. Okay, and cosine of 0 is how much? That is a 1, okay? And then again for y prime, we'll just say that y prime is the value of the derivative at 0, 1. And then what happens here, we get when we put x equals 0, natural log of 1. And natural log of 1 will be how much? That will be 0. And then y equals 1. But 2x is how much? Here we have x. So we have a multiple of x, and x is 0. So that will be 0. So what we got here is this, that, well, this portion has gone out of our way. So our equation has become how much? Simply this. And then if we solve it, what we get is that we get simply, we got 2 times 1, that is simply 2 here, okay? And here we simply get a 1. So what do we have here is that the derivative at 0, 1, or the slope of the tangent line at 0, 1 is how much? Negative 1 over 2. So what the equation would be? The slope is this, so this is the slope, right? And the line passes through 0, 1, right? Okay, let me just write it here. It passes through 0, 1. So an equation can be written as y minus 1 equals, okay, so here we got y minus 1 equals the slope, that is negative 1/2, right, times x minus 0, right? And that gives us what? An equation of the tangent line is negative 1/2 x plus how much? Plus 1. So let's go ahead. If we got, right equation, y equals negative 1/2 x plus 1. So let's go to Desmos, and there I have already cleaned the drawing board. So here I got my negative 1/2 x plus 1, and you can see that this indeed is the tangent line at the point 0, 1. If you want, you can just use the same procedure, the same equation, because here also we can write y as an implicit function and actually a differentiable function of x near 0, negative 1, and we can do this, right equation of tangent line, and so on and so forth. All right.